Triacylglycerols are absolutely the most important storage and energy source lipid. But when it comes to lipids and membranes, glycerophospholipids are the most abundant. Let's take a look at what glycerophospholipids look like. They have some similar features to triacylglycerols. You can definitely see the glycerol backbone, and you can see two long chain fatty acyl side groups. However, notice that at the third position there, we see that there is an alcohol group attached to a phosphate, giving the glycerophospholipids overall a greater love of water. They're very amphipathic, and we often will draw them with a cartoon. You may have seen them drawn with this circle indicating the polar head group, and then these tails indicating the long fatty acyl side groups. And that's a common way to depict glycerophospholipids, particularly when drawing membranes. And you'll notice that I've just put alcohol there as a possibility in the polar head group, and there are a lot of different possible alcohols. But let's actually begin with the simplest phospholipid, which is a phosphatidate. So if we just simply have a hydrogen here, this is phosphatidate. Phosphatidate is kind of the root of more complex phospholipids. And for example, let me start by drawing the first possibility of an alcohol that you might see attached here. And I bet you all are going to start to recognize what it is that I'm drawing, and then we can see how we would name it. Hopefully you're recognizing this very familiar molecule as being the amino acid serine. So what we do in terms of naming it is just to take off this ending. You won't be at all surprised to see this. And then we just call it phosphatidyl serine. But phosphatidylserine is not the only glycerol phospholipid out there, so let's try another one. Don't feel bad if you don't recognize this right offhand. This is called phosphatidylcholine. Phosphatidylcholine is actually the most abundant glycerol phospholipid in the membranes of red blood cells. In fact, there are 21 types of phosphatidylcholine in a red blood cell membrane. And you might think, well, how is that even possible? Well, check out the fact that we have these two separate hydrocarbon side chains, and those can vary, their degree of unsaturation. We've talked about how those might be different kinds of fatty acids, and so we could often see, say, a polyunsaturated fatty acid in the carbon 2 position, whereas maybe a more saturated fatty acid in the carbon 1 position. Let's go ahead and try another. You might actually recognize this one, especially if I could draw a good O there, as being ethanolamine. So this is phosphatidyl ethanolamine. This is actually extremely common in the membranes of E. coli, so one of our epically famous bacteria that many think is pathogenic, but in fact is mostly non-pathogenic. So lots of different types of glycerol phospholipids that comprise different kinds of membranes. As we turn our attention to the phospholipases, we will make a tribute to those of you who love snakes. So the phospholipases break down glycerol phospholipids. These are present in bee and snake venom. We've talked a little bit about components of snake venom so far this semester. But this is a whole new enzyme. This is an enzyme that actually cleaves at the ester linkage of carbon number 2 called phospholipase A2. And there's a whole class of phospholipase A2s, and actually I was jazzed to see that there is an entire book available just on the phospholipases, the phospholipase A2s of reptiles, and so this is an entire book on venoms that is available online. So there are other phospholipases as well, and they are named based upon where they cleave. So phospholipase A1 cleaves at carbon number 1. Makes sense, right? And then we also have phospholipase C and phospholipase D that cleave at the phosphoester linkages. Now, clearly, if red blood cells are cleaved at phospholipase A2, this is going to wreak havoc with membranes in all ways. So evidently, of course, the symptoms, right, that you see of a snake bite or a bee sting, and that sort of highly deleterious effect that it has on the membranes comes from phospholipase A2 and that cleavage that occurs there. So different phospholipases, different locations at which they cleave.
So glycerophospholipids are the most abundant type of lipid within membranes, but the second most abundant type within mammalian membranes is sphingolipids. Now sphingolipids, although they are very common within the central nervous tissues of mammals, are actually generally lacking from bacterial cells altogether. Very, very rarely do you see a sphingolipid in a bacterial cell membrane. So we're going to see them playing a very important role within the membranes of the central nervous system, and we'll particularly think about humans for this purpose. So they're derived from a molecule that you see largely drawn here called sphingosine. So sphingosine is actually a unique alcohol. It's an 18 carbon long alcohol, noting the hydroxyl groups attached to carbons 3 and 1. It's also unique because it has in it a trans double bond, and you notice this trans double bond between carbons number 4 and 5. And the other thing that you might notice about it is that it has an amino group attached to carbon number 2. So sphingosine, this 18 carbon long alcohol, is the building block of the sphingolipids. So you may be thinking to yourself, well, that sort of may kind of look like something that might be a lipid. It's sort of got a polar group up here and a non-polar tail down here. But in order to really become something that resembles or looks a lot like our glycerophospholipids, a couple of other things have to occur. From sphingosine is synthesized a molecule called ceramide. And in ceramide, a fatty acyl group basically becomes attached to the nitrogen bound to carbon 2. So what will occur here is the formation of an amide linkage. So this nitrogen then gets bound to an acyl group. Now we're starting to see how this may look more and more like a lipid, the lipids that we have come to know and love. Okay, if there's a nice long non-polar hydrocarbon tail there, this then makes a molecule that is termed ceramide. So we've now converted sphingosine to ceramide by the addition of this fatty acyl group at carbon number 2, well attached to the nitrogen at carbon number 2. So then from ceramide can be synthesized the entire group of lipids called the sphingolipids. And the sphingolipids can be grouped into 3 different categories, all depending upon what gets bound at this hydroxyl group. So this hydroxyl group will get bound by some polar molecule that'll make the nice large polar head group, and then we'll have the 2 long chain fatty acyl groups. So let's look at the different classes of sphingolipids.
So get ready and hold on for the ride because I am super jazzed for the visual that I'm going to use to try to help everyone understand the 3 different classes of sphingolipids. Now, of course, recall that we have to understand that structure of ceramide, and we've just finished covering that structure. So in order to keep in mind that ceramide is the precursor to the synthesis of all of the sphingolipids, I have a picture of ceramide that I'm going to keep flipping back and forth to as we go through the classes of sphingolipids to show you what changes at carbon 1. That is, what group or entity is bound at carbon 1 to create the different classes of sphingolipids. So let me just bring in that picture of the ceramide precursor and remind ourselves of what that precursor looks like. So this is the structure of ceramide. Now I have left carbon 1 with only 2 hydrogens bound to it to remind us that that's the place where other groups are going to get bound. Said another way, that is the location to which the polar head group will be bound. And depending upon the class of the sphingolipid that we're looking at, the nature of the polar head group or the type of polar head group is going to change. So let's start with the very first of the sphingolipids, looking first at the class that is considered another group of phospholipids. These are called the sphingomyelins, and the sphingomyelins have bound to carbon 1, they have a phosphocholine. That phosphocholine is what causes them to be considered phospholipids. Now don't forget that very much like the glycerophosfolipid that is called phosphatidylcholine, the head group is the same on the sphingomyelins. So to show that off, I'm going to go back to our picture and we're going to look at the phosphocholine that gets attached to that ceramide precursor. So popping back to our picture, we're ready to put on phosphocholine onto that carbon 1, and I have a drawing of phosphocholine over here. We're going to bring that in and check it out. Here it is, the phosphocholine getting added onto that ceramide precursor. So now we can see in its full glory with carbon 1 linked to the phosphocholine entity. This is what sphingomyelins look like. Now you might have heard of them before because I'm guessing those of you who are interested in the neurosciences will recognize sphingomyelins because they're going to think of the term sphingomyelin sheaths. And remember, myelin sheaths, well, let's just say it. There's a lot of sphingomyelins in myelin sheaths. They are the major component of those neural sheaths. Let's look now at the second category of sphingolipids and check out what's going to change getting bound at that carbon number 1. These are the cerebrosides. And the cerebrosides, they have a monosaccharide attached at carbon number 1. For example, the epic monosaccharide galactose. So via a glycosidic linkage to carbon 1, we see a monosaccharide getting bound. And one great example of this is galactocerebroside. So galactose being the monosaccharide. Galactocerebrosides are super important in myelin sheaths as well. In fact, they account for about 15% of myelin sheaths. Let's go back to our picture and see that happen. Let's change the group that is attached at carbon 1 and see if we can check out the change in the polar head group. All right, let's get rid of our choline. Let's just move that aside. And now let's go grab a galactose and recognize that via a beta linkage, we can see a galactose getting attached on here. And I'm straining to show you that it's a beta linkage. Remember that the hydroxyl is above the plane of the ring here on this galactose. We could recognize this as being galactose because of that stereochemistry at carbon 4. So now we basically see here that the bond from carbon 1 to the galactose is what will typify a cerebroside. This is a particular cerebroside, galactocerebroside. So again, it's the change, different polar head group that we see on a cerebroside than that we saw on the sphingomyelins. Nonetheless, both are very important components of myelin sheaths. I hope everybody's been really enjoying reading the Brain Rules book, and we've been getting to hear a little bit about some of the overall morphology of the neural cells, and this helps us further understand the constituents of their cell membranes. Gangliosides are the last category that we're going to talk about. Gangliosides, in place of the where the sphingomyelins had a choline-phosphocholine group, where the cerebrosides had a monosaccharide, gangliosides, they get all kinds of complex. They have oligosaccharides. That is, they have more than one monosaccharide linked to their carbon number 1. I'm not going to draw that all out. We would run soon out of room on our picture.